There we go. Okay, hello. I know I don't have any watchers at the moment, but thought I'd go ahead and record an intro given that, basically this might get posted to YouTube later. Um, yeah, been a long time. Mostly let's see, I was working on that Go application the last time I did a stream, and I kind of burned out really hard on it, mostly because parsing the data format or the file format was it was incredibly tedious and time consuming, and even then not everything worked right, and then figuring out how to traverse it, and yeah, there was just a lot to it, and it was very hard to make any real progress, and so I kind of burned out. But since then, been working on hardware stuff. I thought that I would be showing tonight um, some Raspberry Pi and some LEDs. I'm still going to be showing Raspberry Pi, but instead I'm going to be trying to figure out how to use the USB subsystem. Um, Possibly just as simple as setting up um, serial interface, but I actually think I'm going to start out at the beginning with just trying to figure out how to set up a control endpoint and use the control endpoint to let the computer query the current state of the device. Um, that said, gotta write probably some libUSB code to go along with it. So no idea how this stream is really going to turn out or whether I will even post it. I might be talking right here a whole lot for stuff that nobody is ever going to actually see. Anyway, if this does get posted, and if you are new here, hello, my name is Savani. I'm a computer programmer with 25 years of professional experience. I started this stream as a way for people to see what it's like when a real programmer goes in and how goes in to work on a project, and just how much we also can struggle with some code. Also, I have a cat here and I have a dog here. Might get interrupted by either one of them. The cat seems to be wanting my attention at the moment, and the dog is fast asleep. So with all of that said, um, there can still be some good educational stuff here. I'm going to start out by moving a bunch of code out of the way, but I'm going to want to use it as reference. Might be useful for those of you who are interested in just knowing how to set up a basic Raspberry Pi application using Rust. So if you will give me a minute, I'm going to go back to the background here. And this is the code that we're going to reproduce, but just jumping into it immediately would be really overwhelming. So instead, yeah, okay. I'm going to move that app out of the way. Okay, so one of the things that's really important about Raspberry Pi is that it is not an x86 architecture. Whether that's obvious to you or not, now hopefully it is. It is an ARM Cortex, something like that, architecture. Fortunately, the ARM architecture is very well supported in Rust. It's basically part of mainline. So when you're going to your project, very first thing that you have to do is in your Rust toolchain, you have to actually add thumb v6m none eabi. I don't really know what the thumb v6m is. I just know that somehow that is associated with the ARM architecture. So there we go. And then when you go to set up build scripts for your project, you actually need to configure cargo in ways that you can't really do in the cargo.toml. So instead, you go into .cargo, you open config.toml, and here you specify that this project is going to build using the thumb v6 none eabi target. And then you've got some instructions for it. Like, I don't really know what these instructions are. I just copied them from somewhere. And then this last one is a convenience function that makes it very easy to, like, or sets it up so that cargo run will just copy the file over to the Raspberry Pi, assuming the Raspberry Pi is connected with, or in mass transfer mode, or mass storage mode. In fact, I'll go ahead and boot the Raspberry Pi right now so you can see what that looks like. We'll open up a file system. So you got all of this stuff. And for a Raspberry Pi, there's, at least with the Raspberry Pi Pico, and in this case, the Pico W, there is a button here that you just hold while you power it on. You give it a few seconds, and here we go. It attaches, and there's instructions. So technically, neither of these is a firmware. You're not using the file system or your file system browser to move the new firmware over. You have to use a different application for that. But this just proves that the Raspberry Pi works, and it is currently in a mode to receive a new firmware. With that done, I'm going to back out a level. Go into cargo. This looks really ordinary. There's a couple of things that are different. Obviously, or I keep using that word. It's a bad word. First of all, you need a runtime library for the Cortex ARM processor. You need the embedded HAL, which is a hardware abstraction library that has several common operations that separate you from the fundamental hardware. Embedded I/O, I think I'm not actually using in this case. I think this was, this is for when I'm experimenting with trying to do serial I/O. RP Pico provides some specific things for the overall Raspberry Pi Pico board. So where Cortex M RT is for the processor, RP Pico gives hardware definitions for the board. And it's really designed to plug into embedded HAL. And then this last one, Panic Halt, is present because you can't do a normal Rust Panic on hardware. Like Rust Panic, yes, it's about terminating the application, but it's also about printing out some information to the terminal. You don't have a terminal here. We're running in an OSTD environment, so normal Panic doesn't work. We have to switch it out with something else. Now, I'm going to grab the code that I just moved aside, and I'm going to keep it in reference on another screen. Loading the build environment here. Takes longer when I'm both recording and streaming at the same time. I should have Twitch doing the recording, but I'm not. There we go. And I'll just move that to the side. I'm not going to show you the code that I'm starting with because spoilers. Ooh, no target specified by the manifest. Oh, okay. That'll be fixed probably now. Yep, perfect. Okay. So we're going to start out with a couple of things. First of all, like I said, this is a no STD environment. The standard library just can't work on something as limited as the ARM processor. If you want to be able to have I/O, you have to provide custom I/O stuff. If you want to have memory allocations. You have to import an actual allocator library. Something less obvious is that we're going to do no main. In the case of Rust, when we normally talk about fn main, there's a lot of extra bootstrapping that happens in the Rust runtime beforehand. None of that bootstrapping is appropriate on this hardware. So we're going to write our own entry point, and it's going to look pretty similar to a main function, but we're going to write our own entry point and have that be how Rust starts. Let's see here. A couple of extra things. I think we will start out with... And second, looks like I'm having a little bit of stream issues. Okay, yeah, it's back. Everything just paused for a moment. Gonna import... You know what? Let's just start with trying to program a Dotstar. It's a little lamp that has 3 LEDs in it. It has its own onboard microcontroller, which handles the brightness of the LEDs, but it also handles reading a protocol that's very, very easy to implement. Even if you have to implement it manually, it's super easy. But in this case, we're going to use hardware that's already built into the Raspberry Pi. So I'm going to start out with the panic. So use panic halt as underscore. This is kind of some magic code right here. I don't really understand how this works. All I know is to write it in rote. So now I'm going to import the embedded HAL. And specifically, I'm going to implement the SPI implementation. SPI is the protocol that we're going to use. Don't need to worry about that just yet. I'll go into significantly more detail about it later. Going to import the ability to delay code, and that should be enough for the moment. I'm also going to import the GPIO. The GPIO is not part of the embedded HAL. It's actually part of the Raspberry Pi Pico library because we're getting down into individual hardware. Where is that? Well, I guess sort of ironically, it's re-exported from the HAL. I'm going to have to think about that some other time. Which pins am I using here? That's what a pin diagram is good for. We are using, right, pins 14 and 15, which is GPIO 10 and 11. When setting it up, given that we're going to be using the SPI bus, we have to use pins that are designated for the SPI protocol. And so that basically amounts to anything that says SPIO, or sorry, SPI in it. This is a 2-wire protocol, so we need both the clock signal, so SPI1 SCK, and a data transmission signal, SPI1 TX. If we were communicating with a device that was more complicated, that device could reply to us, at which point we would need SPI1 RX, and then SPI1 CS, chip select. Not relevant in this case. That would be a case where the Pico the Pico itself is a device that could be selected for receiving data. But in this case, the Pico is driving everything. So going back here, I want GPIO 10 and GPIO 11. And there we go. And now we're going to write the entry point, with which we need a particular macro from the Raspberry Pi Pico library. That macro being named entry. So this is our main function, and I don't think that we have to stick to the name main, but I do that just out of convention. But it has to be an unsafe function, and importantly, it has to never return. So we use the exclamation point to indicate this thing never returns. And so I'll go ahead and drop in a loop here. This loop will run forever or until a panic halts all of the hardware. And that's some of the boilerplate. Now we start getting to things that are a little bit more complicated, a little bit more opaque. I'm going to do my best to explain it, but there's areas that are really kind of a bit confusing to me, or for that matter, I just don't really know what I'm doing yet. So, first thing we're going to do is get access to the hardware peripherals. Pack here is, again, a member of the Raspberry Pi Pico library. Despite having the embedded HAL, we're still going directly to the hardware. We're going to have to grab pieces of the hardware and inject it into some of these embedded HAL operations. We'll go ahead and import this. And I haven't dug deep into Pack, the peripheral access, whatever, but I can only assume that there's more than just the peripherals structure. And we are taking total ownership of it. And then from that, we're going to grab, what are we doing? We're gonna build something with some of those peripherals, but first I want to find out what exactly it is that we're building. So I need to find my browser. There we go. Maybe. Where's my browser? Ah. Okay, we're going to build an SIO object. Spoilers, we're basically reproducing. Oh, yes. So we are basically reproducing a lot of this code. And as I guessed, the name of the function does not have to be main. But I'm wanting to know what SIO is. So I'm going to scroll down until I get to... Okay, and it's not listed here. HAL SIO. Okay, yep. So one of the quirks about the Raspberry Pi Pico documentation is that it's got some bad links in between it. And so sometimes when moving between crates, you have to manually traverse it. It re-exports the RP2040 HAL crate. There we go. So let's see here. SIO, single cycle input and output. I don't know what the single cycle part means, but it is definitely input and output. That part I understand. So let's get hold of it. I don't know, well, I don't know what all is compatible with this. So instead of just sitting with I don't know, I'm going to at least take a look at the constructor, which can take any capital SIO, which an IO block provides core local and for the chip. I think this probably just opened up more questions than I knew about. Although it might be we're grabbing hold of, like, there might be like an IO system that is specifically for the peripherals. I'll do a quick skip off to the side because I'm curious now. Probably have to go back to this. RP Pico pack is a re-export from the HAL. Problem is I'm not seeing pack in here. So I might not be able to check embedded HAL for a moment, but I think embedded HAL only provides a bunch of traits. Yeah. Like it provides a lot of operations that are common to various protocols, no matter how those protocols are implemented in the hardware, but it doesn't provide this this pack. I'm not sure where to find it. So we might just have to, or am definitely going to just have to stop my curiosity for the moment. Nevertheless, we grabbed the SIO subsystem for peripherals. We need a watchdog. I don't know why. And now finally we can grab hold of the GPIO pins. And unfortunately, I can't explain it much better than this because a lot of the documentation is still pretty opaque to me. I don't know whether there's more than one IO bank. I don't know what the pads are. What I do know is that now that I have created this pins object, it is pretty easy for me to specify exactly which pin I want. So I'm going to say, we're going to grab the clock pin, which, bring back my documentation. The clock pin that we're working with is this one, SPI1 SCK or GPIO 10. And then when I'm looking at the hardware, it's like pin number 14 on here, but that doesn't, obviously that doesn't match up with the GPIO numbers. So GPIO 10. So pins.gpio 10. And then this magic into function call, we're not going to stick to just calling it into function. This is going to be I may not be able to fully explain it just yet. See if I can get some help from my original documentation. No information available. Let me see if I can just grab one of these and say pins GPIO 0. Yeah, so these GPIO objects have some pretty complicated type signatures. It comes down to that the SPI clock here is a pin, which I haven't imported it, and this pin has 3 parameters. The first one is the pin address, which seems a little bit redundant to have in the type system, but nevertheless, it's there. The second one is the function that's going to be operating on here. So I believe it's going to be... this doesn't look right. Create GP... I'm not sure what the... I think it might be PIO? No. PIO is something different. I'm not sure what the function is going to be. And then there's the pull type. Pull type specifies whether when the pin gets configured, it's set for a pull-up mode or a pull-down mode. If you're new to electricity or don't know electrical engineering at all, I count as new to electricity. Pins can be set up so that either they default to a high voltage state, which on the Raspberry Pi is 3.3 volts, or they can be set up so that they default to a low voltage state. Which one you choose kind of depends on what your application is. If you're set up for a high voltage state, then effectively internally it means that you just get that pin just gets attached to the main voltage wire. So it's almost like you've got the 3.3 volts coming from main power on the Raspberry Pi and going just directly to that pin through a resistor, typically. And then you can do additional operations on, or additional hardware things on the signal that comes off of that pin. And this is actually a valid thing to do even if what you're wanting to do is read the state of the pin. And an example of that, let's say you have a connection that you've made, like just 2 contacts that have come together, and you want to know when that connection gets broken. So you're going to set the pin so that you can read the current state of the pin, but you're also going to set it so that there's current being applied to it. So the pin is going to be pushing power in, and obviously that'll end up ultimately going to ground. Because you're pulling the pin high, but it's going to ground, when you read the pin state is going to be low. It's going to say that there's 0 volts because all of the current being provided is grounded. If you ever break that connection, the pin state will suddenly go high because the pin is providing electricity to this line, but there's no longer a route to ground. I'm actually going to use that on a bike project to detect when I hit the brakes, because the default state would be my brake handles will be closed, and so there'll be 2 wires that are closed together. And if I ever hit the brakes, it'll break the connection. The processor will be able to detect that and then switch on a whole bunch of lights to indicate to everybody around me that I'm hitting the brakes and thus slowing down. I actually imagine that's kind of how a car does things. So let's see here. What are the pull types? Oh, that's not helpful. It is not helpful when the documentation doesn't link correctly. Here we go. GPIO, pull type. It can be pull up, pull down. It can also just float. That's always an option. In this case, what do I want to do? I'm going to pull down because for the SPI bus that indicates it's just kind of the default. all of the hardware is going to be sensitive to a high signal instead of a low signal. So GPIO, pull type, pull down. And I'm still not sure what this one is, so I'm just going to put an underscore there. And then I'm going to do the same thing to get the data line. And that's for GPIO 11. And now that I have the two wires, we're going to create an SPI. Which might be time to explain what that is. But first, let me get all of the, let me make the linters happy. I'm just going to shrink that down. Peripherals is not a module, it is a variable. Okay, so now for an explanation. Do a quick search to see if there's a good diagram available. Maybe on Wikipedia. I'm going to scroll down a bit because what I'm really looking for is a timing diagram, which really illustrates how this works. I'm not seeing one. So maybe I will just draw one. Although it's going to take me a minute to get my drawing application up. But SPI, or Serial Peripheral Interface, is basically a 3-wire interface that allows for two-way communication. Pull this over. Between a host and devices that are connected. Now, there was this will be fine. Here we go. And now I'm going to do something that I hate doing, which is trying to draw with just my mouse. But we're going to do this anyway. We're only going to talk about two of the lines here. We've got the clock line, and then we've got the data line. Oh, wow, yeah. Maybe one day I'll have a machine that's fast enough and has enough ports that I can plug my drawing tablet in while also having my big monitor. Okay. So the way this works, the host controls both of these lines. And for data line, you'll have like a low signal to indicate 0 and a high signal to indicate a 1, and so on. The thing is, though, you have to agree to some kind of timing with your peripherals. With a normal, what we call a normal serial port, that timing is just based on a clock, or is based on an internal oscillator, and you just hope that everything is synchronized. With the SPI bus, the host controls the oscillator, what will happen is the host sets what the next bit is going to be, whether it's going to be low or it's going to be high. And then once that bit is set, the host will raise the clock line. And now it doesn't matter how long the clock line stays high. It could drop down to 0 again and continue on. It is at this particular moment, when the clock line goes high, that the device knows to read what's on the data line. So if the data line is high at the time the clock line goes high, then it's going to read a 1. I'm going to make a new image and format it in the opposite direction. There we go. So let's say that we wanted to send like 1010. So I'll go ahead and draw out the data line, which will be at some point it goes high. We take it back to low, high, low, and then it won't matter what happens after this. Then we've got our clock, and the clock goes along, and once the host knows that it's turned on the data line or set the data line high, the clock will go high, and it might go low again immediately. But at this moment, the device is going to read a 1. At this point, the clock goes on. The host has now set the data line low, so the clock goes high again. And again. Wow. Yeah. Respect to anybody who can do this without making a complete mess. At this point, though, the clock has gone high while the data line is low, so the device is going to read a 0. And this just kind of goes on. So like this right here is a 1, and this right here ends up being a 0. Wait, no, I'm sorry, that is incorrect. Let's erase that. So I get a 1 right here. Right here, we get a 0. Literally nothing happens right here. Nothing at all. Ignore that. It's really easy to do this manually by just manually going down the bits of the data line of the data stream that you want to send, and like manually setting the data, setting the clock, setting the data, setting the clock. But a lot of microcontrollers, and especially something this advanced, has dedicated hardware built in that just makes it a lot easier. I'm not going to save this. And so that's what the SPI hardware that we've just constructed right here does. What we've said is that we want something, or we want an SPI object, and it's working on SPI1 on the peripherals interface. This object is like a nice programming object, but this one right here represents literal hardware. And then these are the 2 pins that we're wanting to use. And it's important to specify the pins because there's 2 sets of pins for SPI1, starting at pin 11 here and running all the way down to pin 20. And there's 2 sets of pins for SPI0. There's 4 through 7 right here, and then over here I can see, in a different order even, 25 through 21. So we're having to specify all of that hardware. And I'm going to save this, and the linter is not going to help me figure out what this underscore should be. I guess because we're just allowed to have that there. So I'm not actually sure what this, maybe over here it'll say? No, it just says pin GPIO 10. Not helpful for my education. Although GPIO 0 cannot be used. Or wait, why does it have an SPI 0 function? It can't. Oh, it can be used for SPI 0. Oh, I see. So if I scroll down to GPIO 10, it can be used as, so this is probably the value that has been set right here. So if I did GP10 SPI1 SCK and I import that, looks like that works. And since this one can only be used for transmit, let's just build it for the fun of it. Got to import this. And it's unhappy with me because it can't figure out what these are good for yet. But in my example code, I don't have anything set there, so it's going to figure it out in a moment. Because next we have to initialize the SPI. Get used to accessing this peripherals.reset. I have not yet learned what it does, but just get used to it. And we need to grab a clock as well, or we need to grab the peripheral clock and, or more importantly, we need the frequency that the peripheral clock is running at. As you can see, clocks isn't defined yet. I've left that out for the moment. We're going to have to define it before everything can compile. The fourth parameter here, I need to look up to see what it is about. Or a third parameter. The third parameter, SPI device, pin layout, SPI new, init, peripherals. This one, they just hard coded it. This one is a 16 megahertz clock, but what does the new function do? What is chapter 4, section 4? That's not helpful at the moment. The new function only takes 2 parameters. What? Oh, I'm thinking about the init function. The baud rate. Oh. Okay. Yeah, this is ordinary baud rate. It's just the number of bits that you want to be sending down the bus per second. I have it set to 1 megahertz. So I'm just going to do that. In a moment, we'll get a compile error because this conversion hasn't been imported yet. We'll get a compile error for this, even after we've defined the clocks, because we have to find the right trait for it. We'll resolve that in a few minutes. And then we're going to do something a little magical. If you start getting into SPI buses, there are 4 modes which really are only relevant for detecting the very first bit that's being sent down in a packet. I just happen to know that the SK9822 runs in mode 1. I don't even remember what that means at this point. So we've had some boilerplate, a whole bunch of boilerplate. We now need to get the clocks. Keep in mind that embedded hardware doesn't have like a continuously running clock the way your computer does. You basically have to initialize it when you start up if you want to use a clock. And in this case, we need access to the clock that is driving the peripherals. We're going to need the clocks in order to be able to do time delays. Like there's a couple of different things here. So let's see here. There's a lot of just kind of magic that is challenging to understand in what I'm about to write, though. So we'll define the clocks object. We're going to call the init function. And this init function is going to do a lot of heavy lifting, but in general, a lot of these parameters are just going to be injecting, here's the hardware version of the clocks for your clock abstraction. We're going to leave out the first parameter for the moment. We'll come back to it. This first clock is an external oscillator that is just built into almost every Raspberry Pi, or at least the embedded Raspberry Pis. I don't know what peripherals.clocks means. It's probably somewhere in the data sheet. PLL, I think, like programmable logic. Wait, I might have that written down in my notes here. PLL is... No. I don't remember what PLL stands for. Couldn't tell you. And then there's something similar for USB. And then we have to give this the resets. And we have to give it a watchdog. Okay, save all of this. Cool, cool. And import the function. And once we've imported it, the documentation isn't really incredibly helpful, but it is still a matter of it's wanting access to a whole bunch of clocks. I'm imagining, though, that between the watchdog and the resets, it'll be using the various clocks and the watchdog to detect that like some part of the system is stalled, and then since it has the resets, it'll be able to like send hardware signals to reset different pieces of the hardware. I'm really just speculating at this point, though. We need to get the crystal frequency. I've already looked it up. It's 12 megahertz. I'm going to go ahead and set it up here. I'm going to spell things reasonably. I'm going to make sure that I wrote that correctly. Yeah, good. And just so you know that I'm not completely just pulling that out of thin air, opening up the documentation that I linked. It is in the data sheet, but in the bottom right of the schematic, you'll find the clock of the Raspberry Pi, a 12 megahertz crystal. So that's where I get it. So let's pass that in. Now all of what we've got right now should be good. Almost. It's getting close. Right, I said that we were going to have a problem with the megahertz conversion because I need to import it extu32, which... Got it. That is in a... What is that in? That's in the RPi Pico crate. It's a re-export from another crate. It's... How deeply is that embedded? Pretty deeply. Can we format? Yes, good. We've got a format now. Fugit? Fugit? I don't know. Hey, let's go look that up. What is this? Time library for embedded targets with ease of use and performance first. Why it's named this, I don't know. But it's, yeah. It's basically equivalent, or it's the embedded equivalent of Chrono. But in this case, like we need conversions, like the ability to convert to megahertz and whatever. I'm gonna jump in. Like duration, number of ticks. In embedded programming, sometimes you need to, efficient shorthands. Oh yeah, in embedded programming you do sometimes need to know about individual clock cycles that are happening on your microcontroller. Not in this case, fortunately. So hopefully we can... Why are we not able to build yet? Peripheral clock unknown field. Looks like I've got a lot of problems still. So let's work on the last one first. Clocks.peripheral clock is an unknown field. Because I did not unwrap the clocks. So now I have to track down where this freq function, the frequency function, is implemented. Could not find RP2040 HAL in RP Pico. Yeah, sometimes the re-exports get a little bit weird. Yes, okay. So this RP2040 HAL, despite what the Rust error message says, it's being re-exported as just HAL. Okay, SPI init cannot be called on disabled SPI1. Well, disabled is not what it should be, but this probably means that I have constructed one of the pins incorrectly. So GPIO 11 any pin, which is required by valid SPI pin. Oh, wait. No. Oh, are these reversed? I need to look up the init function again. Not the init function, the new function. Pins. Pins should be the transmitter and the clock. So what did I do wrong here? It could be that this is incorrect. So I'm going to take that out because normally I don't specify the full-on data type here. Still doesn't like that though. What did I do in my example code? That makes it much happier. So which part do I have wrong? Pulled it. Oh, wait. But that should be the same as that. GP11 unknown, GP10 anything. Yeah, it really doesn't like it when I try to specify all of the type parameters. So I'll take it out because one of the other great things about this SPI utility class is that it can force the bus, or it can force the, or it will automatically configure the pins into the configuration necessary for the bus to function. So if I used those same pins for a different protocol, which I believe those pins also support I2C, which is different. Yeah, they do. I2C is a different kind of nifty protocol for communicating with devices. There's a lot of like sensors and whatnot, things that are really restricted for the number of pins available that I2C is good for, because I2C only requires 2 pins. Excuse me. So we've done all of this. I'm going to take out the GPIO. I'm going to take out some of these unused things, but not all of them. Going to keep a few around. Well, I guess I can take that too. Cool. Okay. Oh. This is a trick that I run into trouble with on occasion. If I tell, let's remove that. So I had a case around here. Oh yeah, right here, where it was like, oh, no wonder things weren't working. Let's back up. Let's back up. Okay. Some of you may have realized what was wrong. Some of you might not, or some of you might not have. I sure didn't. When I told the code actions command, the Rust analyzer, that I wanted to import pin, I wasn't paying attention, and I imported pin, the trait that, or the structure that prevent or attaches something to memory, which is not the same thing. This pin declaration right here is referencing core pin, which pins something or attaches something to memory so that it can't be moved around. But what I actually wanted was something that references the physical pin on the hardware, which is going to be this import, a GPIO pin. So we'll do that, which means that probably now this is going to work perfectly. Well, almost. Pull type is a dynamic object. That's a little odd. Can I just say pull down? Some of the declarations get a little bit odd to me. Yep, there we go. That works. I think I was expecting pull type to just be an ordinary enum. Okay. Anyway, we have something that compiles. It would even run. It just won't do anything. So the last thing we're going to do here then is to make the light on this thing actually work. And before we do that, though, I'm gonna move the camera around, point it at the hardware. That's going to be more interesting than just looking at my face. So for just a moment, I'm going to turn the camera off so that you're not getting disoriented. Almost there. There we go. And let's go full screen on this for a moment, or almost full screen. So the overall configuration of this thing. Raspberry Pi Pico W, we're not using the wireless module. We're using it in just really the most bare bones of forms here. It's also powered on. Oh, right. I remember doing that earlier. Pins 14 and 15 right here are following these two very dark colored wires over to this microchip. This microchip is a logic level shifter. It's receiving 3.3 volt signals from the Raspberry Pi. It's outputting along these two orange lines some 5 volt signals. I'm doing the 5 volt signals because that's what the data lines in the SK9822 require. So one of these pins, in fact, the middle pin on this side of the SK9822, this middle pin is for receiving a clock signal, and then this bottom pin, the bottom pin is or what I'm pointing at is the bottom pin, is the ground pin. This one over here, opposite the ground, is for sending, receiving a data signal. On the opposite side, though, this device will relay clock and data signals to the next one down the line. So the protocol that we're going to send is actually an array of bytes. There's going to be a start frame, which tells the device that it needs to start listening. There's then going to be 4 bytes that address this device, and then all bytes that come after it, it's going to just forward on down the line. So each one will, so if you've got a chain of these things, each one will receive the next round of 4 bytes and forward everything after that, until finally we hit the stop frame. So I'm going to shrink things again and show you what that looks like in more formal documentation. Scroll down here, we can see the physical layout of the very detailed chip. Oh, I scrolled too far. Let's move this over. Here we go. So we've got the physical layout of really the bare bones chip. The rest of this is just to make it possible for me to work with it on a breadboard. Coming down, though, we get the protocol, which is start frame, 4 bytes for the LED 1, 4 bytes for LED 2, 3, and so on, and then an end frame. And the start frame is real simple. It's just 4 zeros. That's it. The end frame is real simple. The start frame is 4 bytes of zeros, and the end frame is 4 bytes of ones. So pretty distinctive. Then we get into a frame for each LED, which is some kind of a 3-1 signifier followed by a sort of global brightness for the whole LED. And then it follows, at least according to this documentation, blue, then green, then red. But I've found that varies quite a bit. I believe this one I determined earlier was red, blue, green. But let's move this over. We're going to set up a byte array for this. In fact, yeah, let lights. Got to check my syntax. For some reason, constant arrays are always difficult for me to remember. Okay, U8. We're going to do 12 bytes. So that's going to be 4 bytes for the start frame, 4 bytes for a single LED, 4 bytes for the end frame. We're going to initialize everything to 0. And this means that we don't have to initialize the first 4 bytes. So I'm just going to ignore those. Instead, I'm going to jump out to the last 4. So lights. And now we'll start at number 4. So 4 is going to be this first byte, the 3 ones, and then 5 bits to handle the sort of overall brightness, 1 to 32. So E0 represents the 3 top bits, and usually I just go with like level 8 or even lower. Now we're going to do the red. Wow, that is not right. Lights 5. Like I said, I think it's red. We'll do it 128. And then blue. Max brightness for this brightness level. And then we'll leave green turned off. And now let's do the end frame. There we go. So this is the data. And now we want to... We're not even going to put anything in the loop. We're just going to send this data, which is going to require... That's what I thought. Save this. The write operation is probably... Nope, it is already in scope. So we should be ready. Nope, not quite. Oh, I forgot to make lights mutable. Cannot borrow SPI as mutable. Cool, cool. Let's load it up. So we'll do a Control-C here. I'm going to... I actually have a button over here that I'm going to use to power the whole thing off. Press and hold this. Power it back on. Give it a second. And in fact, from dmessage, we can see USB storage, a USB mass storage device. Okay, the Raspberry Pi just attached. So now I'm going to cargo run. For good measure, we'll release it. And immediately it lights up, and it looks pretty solid blue to me. So let's rejigger things a little. Turn the blue way down, the red way up, and let's give it some green. Half green. Turn it off. Power it on again. Okay, yeah. The blue is basically gone, and this is giving us some actually kind of nice daylight yellow. Maybe not proper daylight, but you know, I'm kind of getting that feeling. Now, if we wanted to, if we were in a loop, one thing that can be kind of fun here, I'm going to turn the red way back down, set the blue and the green to yellow, but let's animate this. And this is just going to be quick and dirty, but set the brightness to 1, mute step equals 1. That should work. Now, if brightness is equal to 255 and step is 1, then we want step to equal -1. If brightness equals 0 and step is -1, then we want to turn it around, set the step to 1. Then we just want to do brightness plus equal step, and then say, we'll manipulate the blue. So we've got the red set for our static 128. We're going to have the blue coming and going based on the brightness. See if this loads up. Oh, yeah, it did. There's a lot of flicker in the light. I'm not seeing much change in the colors. I have no idea why it's flickering so hard. It could be... Like, it could just be an electrical connection. Breadboards don't have the greatest of all connections, so there could be extra noise in the data signal. Oh. There's also, like, 0 time delay, so we're slamming data through as fast as possible. We'll just have it delay for 15 milliseconds before it goes through again. I need to construct this timer. So we'll come up here. Let timer equals timer new. And it's attached to the clocks. Which clock it's using, I don't really know. There is so much here that I need to learn still. That should do it. So turn that off, power it on, send it. There we go. And I got to look at my screen to see how much. Looks like the camera is picking up some good stuff. Oh no, it's getting hugely overexposed, unfortunately. You can see a little bit of it fading and not fading, but it's really just like over brightness, and yeah, it's not great. I'll reduce the global brightness to see if that helps any. Unfortunately, only a little. Check some... Oh wait, there's some filters. Maybe I can darken this a little bit. Chroma key apply. Scroll. Ooh, I wonder about HDR tone mapping. Let's try this. Reinhard, 300 nits. Sure. Looks like I just stopped the entire camera, so maybe not so much. Oh, wow. My camera is broken now. Well, I guess on that note, we will shrink this. I technically already have a lot of this code already pushed. Like I said, I moved things off to the side so that I could regenerate the code at the beginning. So let me show you where to find that. It's got it on my already existing repository. You don't need to sign in. We can go to Explore. It's in my mono repo. Currently it is on a branch, but I'm going to merge that pretty soon. You go find the Halloween LEDs, source, main. And of course, I'll include this URL in the video description when I post it to YouTube. But all of the code is right here. This particular one has some extra stuff that is not being used. It wasn't quite as organized. And down here is where I was trying to figure out how to use the serial peripheral. But I think what happened here is that it's sending to... It's not sending through, or it's not, this isn't like USB serial. I think it's using the pins as though it's doing serial communication through these pins with another device. So it's kind of the best I can get. But there we go. If you're still with me, thanks for watching. Feel free to check out the code. There's absolutely nothing here that's like secret or copyrighted. I had to do like a lot of copying on my own in order to understand what was going on. And like I said, even then I don't fully understand it. Anyway, I'm going to be resuming these as a weekly get together where I'm just going to be coding on a project and trying to explain what I'm doing. We'll just have some fun. Maybe write some cool projects. In any case, thank you for watching and have a great rest of your weekend and have a great day. Bye.